Hi, welcome to the massive open online course MAT 522. This is an optional video discussing Chapter 5, the applications of second-order linear differential equations, in which we look at the graph of a spring mass system. Now, we recall from the proper lecture video, we have learned and seen the three different models of the spring mass system. The first type, free undamped motion, in which we consider the motion of the spring is perfectly free without any resistance or friction. Second, free damped motion, in which we consider the existence of the damping coefficient in the differential equation. And the third, driven motion, in which we further consider the external forces act on the system. Now, consider the graph of the spring mass system for the first type, free undamped motion. Now, this linear equation, mx double prime plus kx equals to 0, has the characteristic and hence the root of the equation of complex that are alpha plus minus I beta. And therefore, the solution to this type of motion has the form x equals to c1 cos beta t plus c2 sine beta t. And this motion has the graph of the oscillation in trigonometric function. Second case, free damped motion. This has the model of mx double prime plus beta x prime plus kx equals to 0. That is, there exists the damping coefficient beta in the model. Now, in this case, then the solution of the free damped motion depends on the value of the damping coefficient beta and its resultant discriminant beta square minus 4mk. If it is the case that beta square minus 4mk, the discriminant is a negative value, then the associated roots are complex, and hence the motion is underdamped. If the discriminant is equal to 0, then the associated roots are real and repeated, and hence the motion is critically damped. Finally, for the case of the positive discriminant, then the associated roots are real and distinct, and therefore the motion is overdamped motion. Now, these three different types of free damped motion can be summarized into this table. Take a look at the underdamped, the critically damped, and the overdamped oscillation, how the graph of the spring mass system behaves. Now, in order for us to look at the driven motion, the third type, that is, we have the model mx double prime plus beta x prime plus kx equals to external force. This motion will be similar to the free undamped and free damped motion with the additional external force act on it. In other words, the graph of motion will then having similar basic oscillation from the homogeneous part of the equation, in addition to the particular solution due to the external force for the non-homogeneous term. Now, to see how we can sketch the graph of motion, here are some procedures that you may follow. We recall that in the calculus course, in order for us to learn how to plot the graph, we need to first obtain the function. In this case, we solve the second-order linear differential equation to obtain the solution to the spring mass system, that is the function x in terms of t. Then we find the critical point for the time t of the system such that x prime t equals to 0. Here, the first derivative computation is required for us to trace the critical point. After finding the critical point, t, we then test this point by finding the value of the second derivative of the spring mass system. This is to observe its extreme value behavior. If the substitution into the second derivative is positive, then this critical point is a minimum point. Conversely, if the second derivative test gives you a negative result, then this critical point is a maximum point. And finally, if the test happen to be equal to 0, then we say that this critical point is a saddle point. Now, after determining the critical point and its behavior, next we compute more different values for the function x using different time t. And finally, integrate all the findings from step 2 to step 4 on the axis and sketch the corresponding graph of motion. Now, let's see how we can put all the steps into an example. Now, suppose in this example, we are immediately be given a motion of a spring x equals to 5/3 exponent negative t minus 2/3 exponent negative 4t. Now, sketch the graph of motion and finally state the type of this motion. Now, since the function of the spring mass system has already been given, we proceed to find the critical point. That is, we first find the first derivative x prime t from here. This gives us the result, negative 5/3 exponent negative t plus 8/3 exponent of negative 4t. Now, the critical point requires us to equate x prime t equals to 0. Hence, from here, we have the result that is 8/3 exponent of negative 4t equals to 5/3 exponent negative t. Now, by rearranging all the functions and the coefficients on both left and right-hand side, eventually we will obtain exponent of positive 3t equals to 8/5. For us to solve this exponential problem, we put ln on both sides of the equation. This gives us ln of exponent 3t equals to ln of 8/5. The ln of exponent can be simplified into immediately 3t. And this further allows us to find out the time t at the critical point happen to be ln of 8/5 divided by 3. This gives us the value 0.157. This is the critical time for the spring mass system. Next, we test this critical point by finding the second derivative of the function x. That is, from the previous step, x double prime of t is then given by 5/3 exponent of negative t minus 32/3 exponent of negative 4t. What we do here is simply substitute t with the critical point 0.157 that we found just now. So after substitution, here negative 0.157 minus 32/3 exponent negative 4 multiplied by 0.157. We perform the computations and notice that in the end, the answer gives us negative 4.3. This value is less than 0. And hence, based on the second derivative test, we notice that this critical point is actually a maximum point. So we have found the important information from the critical point and the test of the critical point. What we do next is that we compute using more different values of t. Well, the obvious and the simplest one is to begin with t equals to 0. Just in case if we have forgotten the model, x of t is given by 5/3 exponent of negative t minus 2/3 exponent of negative 4t. Substituting 0 into it, then we have the value equal to 1. Next, we substitute using the critical point 0.157 that we found into this model. We obtain 1.069. Next, we try to pick more possible values of t and compute the corresponding result of x. The easiest choices are 1, 2, and 3. So they are all having corresponding value x, 0.601, 0.225, and 0.083. As you can see, the behavior of the value of x from 1 increased to 1.069 and then decrease all the way further as the time increases. And finally, we can plot all this point on a graph using axis horizontal t and vertical axis to be x of t. Simply indicate all the points that we found just now. When t is 0, we have x value found to be 1. And then the critical point 0.157. This has the highest point of 1.069. Indeed, the maximum point that we test in the second derivative. Then we have when t equals to 1, the associated value 0.601, somewhere here. And for the time t equals to 2, we have even smaller value 0.225, say here. And finally, when t equals to 3, this value actually close to 0, 0.083. Now, by plotting all this point on the axis, it is not difficult for us to see if we sketch this curve smoothly, it actually oscillates in this way. This is the function of the motion of spring, x of t equals to 5/3 exponent negative t minus 2/3 exponent and negative 4t. This oscillation is actually overdamped oscillation. And that's it for this demonstration of the graph of a spring mass system. Any graph can be sketched using the same steps as introduced in the previous slide. First, again, find the critical point. Next, test the critical point. Then compute more values. And finally, plot all the findings on the graph. Sketch them using a smooth curve. And you will obtain the desired result. That's it for this optional video. Thank you.